equal to v by r, or v is equal to r omega. So this is the relationship between tangential velocity and angular velocity. The vector form of the equation for tangential velocity can be written as v is equal to omega cross r, where r is the radius vector. So as we have already seen that the direction of omega will be coming out of the plane for anti-clockwise rotation, and for clockwise rotation it is going inside the plane. So we'll denote the direction which is coming out of the plane as this, and the direction which is going into the plane will denote it by this figure. So suppose at this point the object is moving in anti-clockwise direction, so the direction of omega would be this, and the direction of radius vector r would be radially outwards. So the direction of tangential velocity v would be perpendicular to both omega and r. So this is the direction of tangential velocity v. So now you know why its name is tangential, because the direction of velocity v is tangent to the circle at this point. Similarly, at any given point the direction of the tangential velocity v would be tangent to the circle at that point. So which also means that the direction of tangential velocity keeps changing with time. Similarly, we can write the vector form of equation omega is equal to v by r. So here the vector omega, which is angular velocity, would be equal to r cross v by r square. So this is how we can represent omega in vector form. Now if we differentiate the equation v is equal to r omega, we'll get dv by dt is equal to r d omega by dt, or dv by dt will be equal to a, where a is tangential acceleration, and d omega by dt is nothing but alpha, where alpha is angular acceleration. So we have a is equal to r alpha. So these are the two equations that we get. V is equal to r omega and a is equal to r alpha, where v is tangential velocity and a is tangential acceleration, omega is angular velocity, and alpha is angular acceleration. Now let's discuss tangential and normal acceleration. If an object is moving around a circle, there can be two kinds of acceleration which may be acting upon it. One is called tangential acceleration, which is the component of acceleration in the direction of tangential velocity, and the other one is called normal acceleration, which is a component of acceleration perpendicular to its tangential velocity. Now let's understand these two acceleration with the help of an animation. So let's first see this animation. So first let's talk about uniform circular motion. In uniform circular motion, the magnitude of velocity, that is v, remains constant. So as we can see, the magnitude of velocity is constant. So let's say that at time t is equal to t1, the object is at point A, and this is the direction of the velocity vector. Let's say that after some time t is equal to t2, the object is at point B. So here the direction of velocity vector would be tangent to the circle at this point, that is along this direction. So velocity at point A, that is VA, and velocity at point V, that is VB, their magnitude are same. But as you can see that the direction of velocity at these 2 points, that is A and B, they are not same. The direction has changed. So there must be some acceleration which is causing the change in direction. This is the acceleration which we call normal acceleration, that is AN, and the direction of AN is always perpendicular to the tangential velocity. So at point A it will be perpendicular to the tangential velocity and it will be radially inward towards the center. So at A this is the direction of AN, at B this is the direction of AN. So one more thing we can see from here, that the direction of AN is exactly opposite to the direction of radius vector. So this is one point which you need to remember. So in the uniform circular motion there is only one acceleration which is acting upon the object, that is normal acceleration, which is responsible for the change in the direction of velocity vector. Now let's talk about non-uniform circular motion. In non-uniform circular motion the magnitude of velocity vector also changes with time. So the acceleration which is responsible for this change in magnitude is our tangential acceleration AT. So and the direction of AT is along the velocity vector, that is tangent to the circle. So at point A the direction of AT will be along that velocity vector, that is in this direction, and at some other point B it will again be tangent to the circle. So we can see here that if the motion is non-uniform, then there are two acceleration acting upon that object. One is AN, normal acceleration, which is responsible for the change in direction of the object, and another one is AT, tangential acceleration, which is responsible for the change in the magnitude of velocity vector. And as the direction of AT is along the tangent and the direction of AN is perpendicular to the tangent, so AN and AT is perpendicular to each other, and this is the net acceleration of the object. So we can write that A is equal to AN plus AT, and if the vector A makes an angle theta with AT, then the value of AT would be A cos theta and the value of AN would be A sin theta. So as you can see here, tangential acceleration is a particle is responsible for change in magnitude of velocity vector, while the normal acceleration changes the direction of velocity vector. Now let's see the relationship between instantaneous velocity and instantaneous acceleration in circular motion. As we have seen, the velocity is written as omega cross r. So to find the instantaneous acceleration we need to differentiate this expression. So acceleration, that is A, will be dv by dt, which is equal to d omega by dt cross r plus omega cross dr by dt. So A will be equal to alpha cross r, because d omega by dt is nothing but alpha. Alpha is our angular acceleration, and dr by dt is again velocity. So alpha cross r is the tangential component part, that is AT, and we can replace V again with omega cross r. So finally we get A as AT minus omega square r. So AT is the tangential part and minus omega square r is the normal part. So we have an is equal to minus omega square r, and it is equal to alpha cross r. So from the expression of an, it is evident that the direction of an is directly opposite to the direction of radius vector. So the direction of an will always be towards the center of the circle, and that is why it is also called centripetal acceleration. Now we have seen earlier that the magnitude of v can be written as r omega. So we can replace omega with magnitude of v by r. So in this equation, the magnitude of an is nothing but omega square r. So replacing omega by mod v by r, we can write it as v square by r square into r, or mod v square by r. So this is another expression for magnitude of an. Now we will start the chapter particle dynamics. So suppose there is an object which is moving with some velocity v, then all its particles with which the object is made up of, they will move with the same velocity so as to maintain the shape and size of the object. So suppose that we have an object which is moving with velocity v, then all the particles inside this object, any particle which you can think of, they will move with the same velocity v. This is necessary so as to maintain the shape and size of this object. The dynamics of the entire object can be studied by studying the dynamics of a single point inside this object. Now this single point, we'll call it center of mass. So object is considered as a point mass at its center of mass. We'll define center of mass later. So if resultant of all the force acting on a body passes through its center of mass, then all the particles of an object will have same instantaneous velocity. So to understand this, let there be an object with mass m. So there is a point inside or outside this object where the object is considered to be acting like as a point mass. We will call this point as center of mass. So let's say this is the center of mass of this object of mass m. Now suppose there are some forces which are acting on this object, F1, F2, F3. So if the resultant of these forces, let's say this is F,